Okay, so once again, good evening and welcome back to the series of these lectures on what we call online interactive lecture series, which are being organized now for many weeks by the INO project. And in fact, this is a week of 14. And we have today a very distinguished speaker, Professor Sajjad Athar from Aligarh Muslim University, going to speak on Neutrino Nucleus Cross Section and why it is important and what is the current status. Just to say a couple of words on today's speaker, Dr. Sajjad Athar is a professor of physics at the Aligarh Muslim University. He is presently a member of Neutrino Panel of International Union of Pure and Applied Physics. As you know, it's called IUPAP, which is to stimulate and facilitate international cooperation in physics and the worldwide development of science. He's also a member of NUSTEC, which stands for Neutrino Scattering Theory Experimental Collaboration Board, NUTEC's board. And the main goal is to improve our understanding of neutrino interactions with nucleus and nucleons and nuclei, and practically get that understanding in our event generators. He has been recently invited to join SNOW-MASS collaboration, which is to promote long-term planning of neutrino physics in the United States. Now, this is something which I would like to feel very happy to share. Recently, he has written a book along with Professor S.K. Singh on the physics of neutrino interactions, and which is actually published by, which is just out and published by Cambridge University Press. In case you haven't already know about this book, I must say it's an outstanding book. That it's a voluminous book. It is about almost 1,000 pages, 980 pages book, which has 20 chapters and 6 appendices. And it discusses the fundamental concepts of neutrinos, their properties, their interactions with matter, presenting a theoretical framework for describing relativistic particles. It also provides a pedagogical description of the field theory of neutrinos necessary to understand the standard model of electroweak interactions and neutrino scattering from leptons and nucleons. So I would like you all to join me in thanking as well as actually congratulating Sajjad for this great contribution, I would say, to the entire neutrino community, both in the country and abroad. So with that note, I now request Sajjad to start his lecture.
Thank you very much, Satya, for the kind words. And let me thank you also for giving me the opportunity to talk about Neutrino Nucleus Cross Sections, why it's important to understand them and their current status. What I realized that in last week, Indu has already introduced the concept of cross sections, and also she has discussed about the Neutrino Nucleus Cross Sections. But I'm going to take you along the journey where it's explicitly I will talk about quasi-elastic scattering, single pion production, deep elastic scattering, quasi-elastic Hyperon production, etc. And before discussing the interaction of neutrinos with matter, let me start with the general concept of charged lepton-nucleon scattering processes. That means what happens when electron interacts with a nucleon. Then the various processes that we know is that we have the elastic scattering, where this N stands for a neutron, a proton, or we can have a resonant production where that can decay into a nucleon and single pion or multiple pions. We can have associated particle production. We can have eta production. We can have deep elastic scattering. Therefore, these processes are well known from the electromagnetic interactions point of view, and they have, many of them are well studied. And the second important thing which I will use often in this lecture is about the variable X. In general, when we talk about electron-proton elastic scattering or neutrino-proton elastic scattering, in the massless limit of the lepton, we can write Q square as minus 4e prime sine square theta by 2, where E is the incoming energy of the lepton, E prime is the outgoing energy of the lepton, and theta L is the lab scattering angle. The Q square turns out to be is less than or equal to 0. Therefore, equivalently, we define a capital Q square, which is minus of Q square, and that is greater than or equal to 0. Now, applying the same kinematics, I can write P prime square as P plus Q whole square. And this in P square is the mass of the nucleon square, then we have Q square. And in the lab frame where the target is at rest, this is twice m nu, where nu is the energy transfer. Therefore, using this, what we realize, we can write a quantity x as Q square upon Wm square plus twice m nu minus W square. Now, if we are talking about elastic scattering, then W square is nothing but m square. And we have the cancellation of these two terms in the denominator. And simply the quantity that we get is Q square upon twice m nu. Therefore, for elastic scattering, what we say is that since this is true exactly, W square is m square, this x is 1 for an elastic scattering process. But when we go to inelastic scattering, where a delta is produced, then W square becomes mass of the delta square. And since this is a quantity which is larger than m square, this x turns out to be less than 1. Similarly, if you go to higher resonances, the x becomes smaller than 1. And in general, this x lies between 0 and 1. Now, again, let me come to an example of electromagnetic interaction. Suppose if I consider electron carbon scattering and my x-axis is the energy transfer. This is the energy of the outgoing lepton, and say the incident energy of the electron is 187 MeV. This is the scattering angle. What you can realize here that the first peak is the elastic scattering peak, where the energy transfer is very low because E prime is very close to E. But as your E prime decreases, that means the energy transfer increases, then you have the nuclear excitations. And this one, second, and third. And similarly, if you go look another example, that when we are increasing the energy transfer, as you can see, the energy of the incident electron is 194 MeV, while lab scattering angle is 135 degree. When the full momentum transfer square is large, elastic scattering gets suppressed, and then you have quasi-elastic scattering. Why quasi-elastic scattering? Because these nucleons, which are there inside the nucleus, they are not free, they are bound, and they are interacting among themselves, and therefore you have a quasi-elastic scattering peak. Similarly, if you talk about electron alpha particle scattering, then for low, when your x is high towards 1, which is the elastic limit, you can realize that one has the elastic scattering cross section. Now, when we go to the lower values of x, then what we realize that the quasi-elastic scattering starts appearing. And as you can see, that had these 4 nucleons inside the helium nucleus as free particles, then one would expect a peak around 0.25. While again, this is a smeared peak, and that is what we call it as quasi-elastic scattering. And this is because these nucleons are born inside the helium nucleus. As you can see, as we can further go down the value of x, you have again the excitations, and similarly, you can study these processes in the case of electron-proton scattering. Now, what happens in the electron-proton scattering? Initially, you have elastic scattering. This is the black solid line represents the elastic scattering. To put it on the same scale, I have divided it by 15. Therefore, this is the elastic scattering region. The x-axis is the energy transfer nu. And as you can see, if the energy transfer increases, you have the different resonances. And finally, when the energy transfer becomes very large, one has the deep inelastic scattering region. Deep inelastic scattering region is the region where the nucleon breaks up into the jet of hadrons. Therefore, first you have, when the energy transfer is low, you have the elastic scattering. Then you have the different resonances. As you can see, this 1232p33 stands for a delta resonance, which is spin 3/2 and iso spin 3/2 resonance, which marks around 1232 MeV. Therefore, this spin 3/2 and iso spin 3/2 we write in short as P33. Then this is P half, P half, 3/2, etc. As you can see, there are various resonances which contribute in this region. And then you have the deep inelastic scattering. Similarly, when we go to neutrino-nucleon scattering, we start with, say, quasi-elastic scattering, where a neutrino emits a W boson, and that W boson gets absorbed by a, say, if we are talking about a neutrino neutron scattering, this nucleon is a neutron, and in the final state, you have a charged lepton and a proton. Or if you talk about anti-neutrino proton scattering, then you have a L plus, that means if it is an electron type anti-neutrino, then this is a positron, or if it is muon type anti-neutrino, then this is a mu plus. Similarly, if your energy transfer increases, then you can have one pion production, you can have multiple pion production. In the case of anti-neutrinos is scattering on the nucleon target, you can have single Hyperon production, you can have associated particle production, you can have eta production, or when the energy transfer becomes very large, you have the jet of hadrons in the final state, which I am representing it by X. Therefore, let me come to the different interactions one by one. We have simply like AB going to AB scattering process, where we are talking about whether neutrino charged lepton scattering or neutrino nucleon scattering. These are the elastic example of elastic scattering processes. Then we have the quasi-elastic scattering, where neutrino is interacting with a neutron and you have a charged lepton and a proton in the final state. Then you have single pion production. Now this single pion production, you can have a pi plus or a pi 0 or a pi minus, depending upon what particle is with which a neutrino is interacting. If it is interacting with a proton, it can give you a proton and a pi plus, or if it is interacting with a neutron, you can have a neutron and a pi plus, or proton and a pi 0, and so on. And similarly, that would be true for anti-neutrino induced processes. Then you have single K-meson production. That means the strange particle production. This is different from associated particle production, because in the case of associated particle production, strangeness is conserved. Here you can have a K plus production, K0 production, or K minus production, or K0 bar production in the case of anti-neutrinos. Then for anti-neutrino induced process, you can also have a single Hyperon production, where you can have a sigma 0, you can have a lambda 0, or a sigma minus. These processes are not possible through neutrinos because of delta S, delta Q conservation rule. And therefore, this type of, as you can see, that if I apply a process, write something like neutrino interacting with a neutron, and we have L minus and sigma plus, although we are conserving baryon number, charge conservation, etc., but Q is plus 1 for the hadrons. As you can see, delta Q is plus 1, the change in the charge, and the change in the strangeness number is minus 1. Therefore, if delta Q is plus 1 and delta S is minus 1, these are the forbidden processes. Therefore, for the neutrinos, these are not allowed processes. while these are possible in the case of anti-neutrino induced reactions. Therefore, when we talk about inelastic scattering process, there are various processes which contribute to the particle production. Similarly, you can have eta production, where neutrino interacts with a neutron and you have an eta in the final state, or you can have associated particle production where delta S is conserved, and similar type of processes you observe in the electromagnetic interactions and strong interactions, etc. Then you can have neutral current induced processes where you have a neutrino in the initial state and neutrinos in the final state. Therefore, these are the various inelastic scattering processes which contribute to the lepton production, or in general, they contribute to the charged particle production. Therefore, these two curves you often see in most of the talks, and the right-hand side is the picture for the neutrino-induced reaction, and the left-hand side is for the neutrino-induced reaction, and the right-hand side is for the anti-neutrino-induced reactions. If you see that these are the different experimental points with the error bars, and as you can realize, these error bars are quite large. Then we have the theoretical curves. This dashed line is for quasi-elastic scattering, dashed dotted line is for the resonance production, and this dotted line is for the DI scattering. Therefore, if you add these three, you will get this solid line. This is for neutrino and this is for anti-neutrino. But what is important, that when we talk about resonance process, there are many reactions which contribute to this energy region. And that is why if you talk about whether the energy region of Dune or energy region of Minerva, or even the energy region of Nova, T2K, Mini Boon, etc., all these experiments have very wide neutrino energy region. And if they have got an energy region of say 1 GeV to up to 10 GeV or 15 GeV, then the contribution to the cross section comes from all the possible channels. And therefore, it is important to understand the contribution of each individual channel to the total scattering cross section. In general, in the case of electromagnetic interaction, where you have an electron beam or a photon beam, precisely you measure the total scattering cross section. But in the case of neutrinos, you don't have the precise measurement of the cross sections. In fact, almost 25 to 30% uncertainty in the systematics arises due to the lack in the knowledge of neutrino nucleus cross section. That is why when one is going towards precision era, wants to measure precisely the neutrino oscillation parameters, or to want to study CP violation in leptonic sector, it's quite very important to precisely understand the contribution from the different channels to the total scattering cross section. Now, when we talk about resonances, then as you can see, there are many resonances which contribute to the, for example, I have shown here for the single pion production. If you have a delta, then all the deltas decay to pions. But if you take the example of different other resonances, then these show the different branching ratios. And I will come to that, what the uncertainty we get from the different resonance production when one tries to calculate the scattering cross section. Therefore, when we talk about resonances, there are various resonances which contribute to the scattering cross section. When we talk about inelastic processes, there are many processes, various kind of processes which contribute to the scattering cross section. And the important point which I have told you that the good understanding of neutrino cross section is necessary for the neutrino detection, energy reconstruction, neutrino flux calibration, determination of backgrounds, reduction of systematic errors needed in the quest of CP evaluation. And for all these, we need a precision which should be less than 5%. And this you can further understand by looking at these two pictures which I am going to show. One is at neutrino energy of 3 GeV and another picture I will show for the neutrino energy of 7 GeV. As you can see, there is the first diagonal line is the region which shows the elastic scattering region. W is Mn, mass of the nucleon, and Q square is twice Mn nu. On your X is 1. But as you go towards the right hand side, what you realize, you have the single pion production threshold, then you have the delta production threshold. Then if you go further higher towards this region, you have the contribution from higher and higher resonances. And then finally, you reach to a point which you call it as deep inelastic scattering region. This deep inelastic scattering region, in literature, there is a debate on it, that what is the region which we call as deep inelastic scattering region. The recent literature says that deep elastic region are those regions where Q square is greater than 1 GeV square and the center of mass energy is greater than 2 GeV. And that means if Q square is greater than 1 GeV square, this y-axis is Q square, then this is here, this is only the DIS region at E nu equal to, let me see, there are few questions. And what you realize that this is the shallow inelastic scattering region, and these are not presently well understood. Then this is the region which in literature has not been well talked about. This what we call it as soft DIS region. Therefore, elastic scattering region we understand. Then we have the non-resonant background region, which I will discuss. Then we have a delta production region. Then the region which we can show by the different diagonal lines for the different resonances, which we call as the region of shallow inelastic scattering. Then you have the DIS region and soft DIS region. Therefore, if you have got, say for example, Minerva, they were using low energy. That low energy corresponds to an average energy of 3 GeV, and now they have performed experiment using medium energy beam, which I am going to discuss in my next slide. This is around 7 GeV, and as you can see that once you go from 3 GeV, you can see that DIS contribution is quite low. But when you go to 7 GeV, you can realize that the DIS contribution becomes quite large. Then you have again the SIS region and the soft DIS region. And the important point is, presently most of these regions are unknown. The first region I talked about, the elastic or quasi-elastic region. Then you have the baryonic resonance region. Then the region translates to a shallow elastic scattering region, and this is the deep inelastic scattering region. And since we want to understand precisely the cross sections, therefore what has been suggested recently in the different neutrino conferences and workshops, that since all these experiments are being performed in nuclei, like if INO is going to use iron nuclear target, Super K is using water, Minerva is using carbon, iron, lead, etc. One, it is very important to understand the nuclear models, the uncertainty of which produces uh, significant uncertainty in the determination of the event rates, then it has been suggested that it's also important to provide results for neutrino hydrogen or neutrino deuterium target, because even at the nucleon level, in the resonance region, we don't know many things, and we can only understand them if there is a measurement of neutrino proton or neutrino deuterium scattering cross sections, because the measurements which were done are almost 40 years old. They were performed at Oregon National Laboratory and Brookhaven National Laboratory, and the error bars are quite large. Therefore, and these error bars translates again into the errors when one calculates the neutrino nucleus scattering cross section. The other thing that has been suggested also is to determine the vector part of the interaction. It is also important to perform scattering experiments with charged lepton on nuclear targets. Therefore, it has been suggested recently that uh, there are challenges at all fronts. For the theoretical people, there is need for better nuclear model. Then we need from the experimenters the scattering cross sections for neutrino hydrogen or neutrino deuterium targets, and also we need to determine the vector form factors, the experimental results in the kinematic region of present neutrino physics experiments for electron nucleus experiment. And this is an article which we have recently written. It is going to be published in Journal of Physics G with Jorge Morfin. Here I have discussed what are the problems in the shallow inelastic region and the deep inelastic scattering region. First 10-15 pages discusses the basic points which is needed, which is required to have attention from both the theorists as well as experimentalists. Now let me come to the important point. When we talk about any event rate, then that event rate is the convolution of the scattering cross section, the flux, neutrino flux, number of target particles, and the time of interaction. Now, in general, if we are talking about 50 kiloton target, we know how many protons are there or how many neutrons are there. For how many days we are going to perform the experiments, we know what is the time we are going to for which we are going to collect the data. But these are the two important points which has to be understood very well. And the lack in the understanding of the cross section results also in the uncertainty or in the determination of the neutrino flux. Therefore, not only the uncertainty comes into the picture at the first point where I am showing the scattering cross section, but the uncertainty or lack in the knowledge of the cross section also translate into the determination of the neutrino flux. As you can see here, for example, I have shown Minerva flux. This Minerva flux has very broad energy region. Or the right hand side shows the atmospheric neutrino flux. And as you can see, the region of atmospheric neutrino flux is also quite broad. Therefore, and this is particularly I have shown here for INO, directional average, for Kamiokanda mines, for South Pole, and for Shalmi mines. As you can see, we have the different fluxes, and that is because of the geomagnetic effect. That is entirely a different topic. And what is important is that there is a wide energy region from which we get the contribution for the cross sections. And if you look at the simple quasi-elastic kinematics, where a neutrino interact with a neutron and we have a lepton in the final state and a proton. Because in any experiment, we never see a neutrino. What we see, either we see a lepton, or along with lepton, we see a pion. In general, the fluxes are determined using this kinematics. But here I am showing the kinematics for a free neutron, which is placed as a target. Now, if you have a free neutron, then directly from two-body kinematics, you can determine the energy of the neutrino by seeing the or measuring the charge of the outgoing lepton and by looking at the angle theta. So therefore, if you know EL and theta for the outgoing lepton, from here you can infer what would be the energy of the incoming neutrino. But what happens when you are not performing experiment with free nucleon target, you have bound nucleons, then the nuclear effects come into play. For example, if I am talking about T2K flux, which has a wide energy region, what you see that what people do in literature, that they put a binding energy correction to the neutrino energy to take into account nuclear effect. But just by see, if you look at the previous slide, here the neutron was free and you had the simple expression. But when you are talking about a nucleon target inside a nuclei, then one is introducing binding energy. But binding energy is not the end of a story, because these nucleons are in motion, which we call it by, they are defined by the Fermi motion, about which I will talk about later in this talk. And this Fermi motion introduces an error of about 60 MeV. Then you have quasi-elastic like events. Although what you are seeing in a process where a pion is produced and that pion gets absorbed inside the nucleus. About this quasi-elastic like events I will talk about later in my talk. And this quasi-like events produces a shift in the energy of 150 MeV in the energy region of 1 GeV. Therefore, what you can realize from these spectrum, that if I have the uncertainty of 150 MeV or 200 MeV in the T2K spectrum, or which peaks around here around 600 MeV or 700 MeV is the peak of the T2K spectrum, and I am seeing an uncertainty of 40 to 50 MeV from Fermi motion and 150 MeV from the quasi-elastic like events, then that means flux which we are talking about at 800 MeV could be 1 GeV neutrino, or that could be a smaller energy neutrino. Therefore, it is important to even determine, while we want to talk about the flux, neutrino flux, it is first important to understand how much is the neutrino nucleus cross section before we talk about exactly the flux with a very less uncertainty, because just by putting the near and far detector does not exactly cancels these errors. Now let me come to the basic point, the quasi-elastic scattering. This is the quasi-elastic scattering for a neutron target, and as you can see, you can have an electron here and a proton here. If it is a neutral or elastic scattering process, then you have a neutrino in the initial state and neutrino in the final state. Then we talk about the nucleons bound inside the nuclear target, where you can have quasi-elastic scattering or you can have elastic scattering. Therefore, here I am showing that the nucleons are bound inside the nuclear target. And let me just talk about the quasi-elastic scattering process. Therefore, what neutrino has done, it has emitted a W boson, and that has got absorbed by a neutron. and these are the other spectator particles which has not directly participated here, but they are nucleons, and all these nucleons are strongly interacting particle. Therefore, these interactions play important role in the determination of the cross section. It is not free neutrino-nucleon cross section. Therefore, what is important first is that these nucleons are bound. One has to consider the binding energy effect. Then they are in motion. We have to consider the Fermi motion effect. Then all these states, which I will talk about above the Fermi C, they won't be allowed. There will be polyblocked states. Then these nucleons are strongly interacting particle. There will be multi-nucleon correlation effects and final state interaction effects. I will come to those figures again. Now, if I am writing the neutrino-neutron scattering reaction and the transition matrix element for that, then you have the hadronic current and you have the leptonic current. These hadronic current are described in terms of the vector and axial vector form factors, because these nucleons are hadrons, they have got a structure. And the important point is, if we don't consider second class currents, then what we talk about only the F1 and F2 form factors, which are determined in terms of the electric and magnetic Sachs form factors determined from electromagnetic interaction, and axial form factors from the weak interaction. Therefore, what is actually happening is that a nucleon is bound inside the nucleus. Therefore, the first important point is the nucleon binding. The nucleons in the nucleus are bound and they are off mass shell. This affects the free particle kinematics, and the peak of the energy distribution is shifted from what you get if you assume only the quasi-elastic limit. Then the Fermi motions, the nucleons in the nucleus are moving with a finite momentum. In Fermi gas model, this momentum is bounded by a maximum momentum called Fermi momentum. For example, if you look at the Gini code, for carbon, they are using 220 MeV. If you go to iron, it increases with the increase in the mass numbers. Some you will find 230 MeV, for lead 235 MeV, and so on. Therefore, you have the Fermi momentum. Then you have the polyblocking. In the language of many body field theory, that all states below the Fermi C, they are completely occupied. If you talk about any interaction that is taking place, the nucleon has to move above this Fermi C. But all these states are not free, and therefore what we say that in nuclear reaction, the nucleons from a certain field state are excited to a higher unoccupied state depending upon the energy transfer, creating a hole in the Fermi C and a particle above the Fermi C. Therefore, before the interaction, all these states below the Fermi C are filled, and if the interaction has taken place, then the particle has to move above the Fermi C, and this we call it as one particle, one hole state. Now, what is the important condition? That the initial momentum of the nucleon, which is below the Fermi C, must be equal less than the Fermi momentum. That is the reference momentum of the nucleon in the Fermi C. And the final momentum, since the nucleon has to move above the Fermi C, must have a momentum greater than this Fermi momentum. This is the nucleon momentum and this is the momentum transfer. This should be greater than the Fermi momentum. This is the important criteria if you consider the Fermi gas model. Now, this expression deals with the differential scattering cross section for free neutrino-nucleon scattering, which is described in terms of the leptonic tensor and the hadronic tensor. This is just the energy conservation delta function. But when you go inside the nucleus, then you have to consider these effects into account. And when you take these effects into account, that the Fermi momentum of the initial nucleon should be less than the Fermi momentum reference Fermi momentum or the momentum of the final nucleon should be greater than the Fermi momentum and the binding energy effect. This is the basic model which we call it as the Fermi gas model. But what happens, since there are nucleons in the nucleus, therefore these nucleons are a strongly interacting particle. Constantly they interact among themselves through the pion and rho exchanges. And therefore, when they interact through pion and rho exchanges, they modify the form factors. In fact, and what that is what we call it as the RPA correlations, random phase approximation correlations, where the form factors gets modified due to the presence of other nucleons in the nucleus due to this. Basically, this is also a multi-nucleon correlation effects. And what has been observed, here I have shown the cross section for the different nuclei, carbon, argon, iron, and lead for neutrino-induced process. And on the right hand side, we have anti-neutrino-induced process. As you can see that this is the ratio for the nuclear cross section per nucleon, per neutron to free neutrino cross section. The right hand side is cross section per proton upon the free anti-neutrino proton cross section. As you can see that because of the Fermi motion and polyblocking effects, binding energy effect, there is a reduction in the cross section. That is, this reduction you can directly see at lower energies, even that they are present even at 800 MeV, or even that is present up to 1.5 JeV. And then one takes RPA correlations into account, then there is a further reduction which has been shown by the dotted line in the cross section, and this reduction is quite significant. This is not only true for muon neutrino or electron neutrino, or rather it is true for both of them. The left hand side black lines are for neutrino induced process, and the right hand side with the dashed blue line are for the muon neutrino induced process. Therefore, electron neutrino, the threshold is low. Therefore, because you have an electron in the final state, therefore the curve starts from here, while for muon the curve starts from here. If you talk about a tau-1, then tau-1 has a threshold of 3.46, and that is much to the energy region which presently I am discussing here. That is why I am not showing here the neutrino tau-1 interaction. That is again a different topic, different energy region which has to be dealt with. Therefore, what you can see that with the increase in the mass of the nuclear target from the carbon to lead, there is a large reduction in the cross section. And this large reduction first is because of the binding energy and Fermi motion effects, and then further due to the RPA correlation effects. And these have been recently discussed in different Monte Carlos.
Sajjad.
Yes.
Yeah, if I can interrupt you, there's a question in fact from Professor Athar. You can see that is there on the chat window in the Zoom, but just quickly I can read that for you. Is the effect of pairing interactions of nucleons in the target small?
No, that is what I am going to talk about.
Okay.
Okay. I think, can I take the question in the last?
That's fine. No, I thought it may be a contextual.
Because I am unable to see the questions.
No problem. I
am very sorry for that.
No issue. I just thought it is a contextual one. Normally, all questions are taken at the end. You can go ahead.
Okay.
Yeah.
See here, this is the picture. A conference was held in 2011, and then a group was formed. In fact, Aligarh is also an active part of that new state group, where it was first decided to collect all the results of the theoretical cross section for quasi-elastic process, where one takes into account Fermi motion, polyblocking, and nucleon correlations, etc., in the different versions of Fermi gas model and the other models available in literature. What we found that if we collect all these different theoretical models, the cross sections almost are very close by. But around the same time in 2009, mini boon result had come, which I think Indu has also talked about. Mini boon result had come, and this cannot be explained by simple considering a theoretical picture like this. Around the same time, two papers came, first by Marco Martini, where they first applied their results to electromagnetic interaction, and then they applied their results to neutrino interactions. And then later, a similar work was performed by Juan Neves, the Spanish group. And what they said, that there is a further contribution of two particle, two hole excitations. That means two nucleon, in general here, whatever I have talked about in the case of quasi-elastic scattering, is that a neutron is sitting inside the nucleus and a W boson is interacting with that neutron, and with the interaction it is taking the particle to above the Fermi sea. But and then modification in the through the RPA correlations, we are taking those to that neutron target. But here what they considered that two nucleons, they are already talking with each other, and in the meantime a W boson gets absorbed. Now this means that if one considers there are many nucleons in the nuclear target, there can be 3 particle 3 hole excitations also. There can be 4 particle 4, because these are strongly interacting particles. Therefore, if we are saying that 2 nucleons are there, if I am talking about carbon nucleus where there are 12 nucleons, I cannot say that only 2 nucleons are talking with each other and there is a contribution of 2 particles and 2 holes. The interaction is arising because of that. There could be 3 particle 3 hole, or in general there can be n particle n hole contribution. But what has been found in these Martini's paper, that the contribution from the higher n particle n hole contribution, that decreases significantly, and they found that there is a significant increase in the cross section when one considers 2 particle 2 hole interaction, and that is this line which passes through the mini boon results and explain the data very well. Then you have the cyan line. This is by the Neves group, and that also agrees well with the mini boon data. Although, as you can see, these two different theoretical models don't agree within. That means there is a difference within a few percent, and that difference still exists. Now let me come to the people who are doing the analysis and who talk about the generators. Now in the market, if you see the different generators, they are always the Genie with the different versions. Genie 2.80, 2.8.4, Nuvro, Nuit 5.3.2. And as you can see that Genie 2.8.0 has Smith and Moniz Fermi gas model with axial dipole mass 1 GeV, and they consider correlations as well as 2 particle 2 hole from the Valencia model. Then Genie 2.8.4 has RPA correlation from Valencia model as well as 2 particle 2 hole from the Valencia model, and they tune their model to Minerva CCQE data. See here, again, a tuning is being done. You are trying to explain the experimental data, and that is why you are tuning something. Then Nuvro, they are using Fermi gas model, local Fermi gas model, plus RPA, plus 2.2P2H, then MA 1.16 GeV. Now to the students who are doing such type of analysis, I must tell you that if in the low energy region of around 800 MeV, 1 GeV or around that, if you increase the value of MA say by 10%, the increase in the cross section is about 10%. Or if you increase it by 15%, this increase in the cross section is by 15%. Therefore, as you can see, one is using 1 GeV and another guy is using 1.16 GeV. Similarly, you have Newt And similarly, you have NUT 5.3. These basically T2K and Super K people are using NUT. Uh, and as you can look at all these numbers, there is a difference. And this difference is quite a lot. And then that means even with two particle two hole, we don't understand much all the experimental data. And this you can realize by looking at this analysis. This analysis was performed by Wilkinson group. And what they did, they had relativistic Fermi gas model, relativistic RPA, then two particle two hole of Valencia model and MA 1.01. And they tried to fit the Minerva data as well as Mini-Moon data simultaneously. As you can see, these are the Minerva data for neutrino and anti-neutrino, and these are the different theoretical model: RPA plus two particle two pole, a spectral function, two particle two hole, relativistic Fermi gas model, and exclusively the contribution from two particle two hole. As you can see, if the blue line RPA with two particle two hole is explaining the Minerva neutrino data, it is not well explaining the Minerva anti-neutrino data. Or simultaneously, since they fitted for mini-Moon, as you can see, this RPA plus 2P2H is away from the Mini-Moon data in the peak region. And there is more crisis for the anti-neutrino scattering. As you can see that these numbers, experimental numbers, are quite low from the theoretical numbers. This is another paper that has got published by Minerva collaboration, where they have plotted iron to hydrocarbon and lead to hydrocarbon. The beauty with the Minerva experiment is that they can perform EMC kind of studies. That means the heavy nuclear target to light nuclear target, just to see that how much is the nuclear effects. But as you can see, that these are the various theoretical models and which are being used in the Monte Carlo generators. And first of all, there is a difference among these theoretical results, and then even with these different theoretical results, the experimental data are away. Then this is see, when you are talking about two particle two hole or T2K energy region, or in general Minerva energy region, there are contributions from the different channels. What had happened in 2019, Mini-Moon did an analysis for kaon decay at rest experiment, where the particle kaon is decaying at rest. If it is decaying at rest, then you know that the energy of the neutrino will be unique. And this energy was 236 MeV. This energy is below the two particle two hole threshold. And what they did, they measured the charge current scattering cross section to be 0.27 plus minus this, plus minus this. As you can see, there are large error bars. We performed such type of theoretical analysis and compared with the different theoretical models available in literature. And we found that with more sophisticated models, we are away from this 0.27. As you can see, 0.27, if I will plot, this will be away from these theoretical curves. And this black solid line, this is representing the RPA effects. Therefore, you can see that even in the low energy region, what to talk about two particle two hole or multi-nucleon correlation effects, it's really till now we have not well understood the low energy part of the interactions. Then let me come to the pion production. As you know, I have already discussed, there are various modes of pion production, and the differential scattering cross section again contains the transition matrix element square, about which Indu has spoken. And this transition matrix element square matrix element is written in terms of the leptonic current and the hadronic current. Now, when we talk about the resonances, then we have a delta resonance or we can have any star resonance or any another resonance, and that resonance then decays to a nucleon and a pion in the final state. For example, here I have considered a delta resonance, and we have only the information about the delta resonance. We have very little information about the higher resonances for the axial vector sector, and even in the vector sector, there is quite limited information. Now, when I talk about delta resonances, this is how you write the hadronic current in terms of the Redeta-Schwinger spinors, N-delta transition vectors, and the Dirac spinor for the incoming nucleon. And this for positive parity states, this is given by vector minus axial vector contribution, the gamma 5 factor, and for negative parity states without a gamma 5 factor, because all these resonances have got different parity. Now, when we talk about these N-delta transition form factor or N resonance transition form factor, these are given in terms of vector form factors, which are determined through the electromagnetic interactions processes. And then we have the axial vector form factors, which are determined from the weak interaction processes. And there is quite a lot of uncertainty, especially in the higher resonances contribution when one considers that into account. Besides that, I have also talked about the Q squared nu curve, where I told you that different non-resonant background contribution must also be taken into account, because, for example, if you have don't have a resonance in the final state, that you have a nucleon, and that nucleon as propagator gives rise to a nucleon and a pion. This can be possible through S-channel process or U-channel process, or in effective field theory that may arise through pion pole, or pion and flight, etc. Then besides that, when for example, a delta is produced, delta is a strong interacting particle. It has been found from the electromagnetic interaction that when delta is in the nuclear medium, there is a big change in its mass and its width due to nuclear medium effects. Therefore, there is a reduction in the cross section because of the delta modification in the mass and the delta width. The free delta width is 120 MeV, but when you consider this delta to be in the nuclear medium, it becomes different from 120, and that difference brings a big change in the scattering cross section. Besides that, there is another important point, that suppose a resonance has got formed. Now that resonance has to decay into a pion and a nucleon. In a simple picture, had there been no spectator particles, this pion will directly come out. But in reality, what is the important point? That there are other nucleons present inside the nucleus, and therefore pion, which itself is a hadron, and nucleons, they are hadron. Therefore, there will be a strong interaction between a pion and a nucleon, and that is what we call it as the final state interaction. Therefore, suppose I have reaction something like that. A pi plus had interacted with a neutron, and you have a pi 0 plus proton, and then a pi 0 with proton, it gives another type of pion here. Then you have another type of pion here. Therefore, what is happening, since there are many nucleons inside the nucleus, this pion is not directly coming out. This has final state interaction. And because of final state interaction, even it can change its charge. A pi plus plus interacting with a neutron can become a pi 0 plus p. And again, a pi 0 plus p can give rise to a pi plus plus n, and so on. Therefore, FSI effects should be taken into account. This is one effect. The other effect is more interesting, and that is what we call it as quasi-elastic like events. See here, since pion, they are mesons, we don't require any lepton number or baryon number conservation. We require that my proton or total nucleon number should not change. What happens? Suppose a pion has got produced, and on the way through a process something like this, pi plus has got absorbed by a neutron, and then you have a proton in the final state. Therefore, in principle, you were doing a calculation for a pion in the final state for a free particle scattering. But when you have taken that particle inside the nucleus, a nucleon inside the nucleus, because of the final state interaction, that pion has got absorbed. Therefore, if the pion has got absorbed, what you will see only a charged lepton in the final state. And if you are seeing only a charged lepton in the final state, that will mimic a quasi-elastic event. Therefore, this is why this is called a quasi-elastic like events. Although you are talking about a pion, production of a pion, although pion is getting produced, but it is not coming finally as it was coming out here or directly without the spectator nucleons, it was coming here. It is getting absorbed, and this produces lot of reduction, almost by 15% in the scattering cross section when one talks about the pion production in the final state. Therefore, this is basic results that this dotted line is when we don't consider any modification in the delta property. This red line is when one considers the modification in the delta properties, and this green line is when we consider the final state interaction of the pions. As you can see, first we have the reduction because of the modification in the delta properties, because of many body effects, and then we have a further reduction in the pion production. When we want to see a pion, there is an absorption of pions. Therefore, these two together puts a large reduction in the scattering cross section. Now, for the pion production also, there are various theoretical models available in the literature, and this was also done by us in New in conferences. And what you can see that this is the result I am showing from Minerva, because this is the latest one. These are the theoretical results from the Monte Carlo, and these are the experimental data. And as you see, even in the case of pion production, we don't understand the cross sections very well. As you can see here also, I am showing the different theoretical results, and these are the experimental numbers. And as you can see, no model is able to explain this Minerva data in the complete kinematic range. And here, this is an interesting result, which is from Minerva, where they have shown CC 1 pi plus production, CC n pi plus production, 1 pi 0 production for anti-neutrino and neutrino. And as you can see, this is the ratio Monte Carlo to the data. And as you can realize that there is a lot of uncertainty in the pion production results. Therefore, it's very important. That is why I told you that 25 to 30% uncertainty arises in the cross section, in the systematics, due to the lack in the understanding of the cross section. Then similarly, you have the deep inelastic scattering cross section. Now, in general, almost 15 years ago, when people started the discussion on neutrino nucleus scattering cross sections, nuclear effects in the quasi-elastic region or the inelastic region, everybody was serious about those two regions. But people were thinking that in the DIS region, the medium effects would be quite low. That means it will be less than 2-3%. What we showed in the last 10 years, that really that depends upon Q square, that depends upon the cuts on the center of mass energy, the two figures which I showed you. And there is also important, it is very important to understand medium effects in the deep inelastic scattering region. Now, when you write the deep inelastic scattering cross section, that is written in terms of the structure functions. These free nucleon structure functions are in terms described in terms of Pion momentum distribution function. And these are well determined from the electromagnetic and other interaction processes. And for this also, there are various parametrization available in literature. But what we have realized that those different parametrization, whether that is by MRST group or CTEC group or GRV group, Gluck, Ria, Vogt, and others, they don't much affect the cross section. Now, the understanding of nuclear effects in the DIS region First, it started with the observation of EMC effect, which was observed with the electron and muon beams, where the nuclear structure function to the ratio to the deuteron structure function was plotted. And this is the famous curve where which describes the anti-shadowing region, the very low X region, then the anti-shadowing region, then the EMC region, and finally the Fermi motion region. And these are basically the different nuclear effects which arises even in the DIS region. And that is why we studied these nuclear effects in the DIS region, and we found that it is quite significant in the different regions of Q square and W, and it's important to understand it. And if you can look at the different phenomenological fits, because in the market there are many phenomenological parameterizations. There are almost scores of parameterizations where nuclear effects in the DIS region have been studied, but most of them have been studied using lepton nucleus scattering, DIS scattering, proton nucleus scattering, Brilliant data, etc. But there are two theoretical groups. One is Collagen and Petty, and another is our group, who have studied medium effects in the weak interaction as well as electromagnetic interaction processes recently. And why we are emphasizing it? Because based on these phenomenological analysis, there are two different groups. One is by Pakunen and Salgado. They say that there is no difference in the in nuclear medium effects arising in the electromagnetic interaction and the nuclear medium effects arising in the weak interaction process. But there is another group which is more acceptable now in literature, CTEC Karlsruhe group, where they say that neutrino nucleus DIS medium effects are different from electromagnetic nucleus DIS scattering effects. And this should also be in general true, because in the case of neutrino, you have the axial vector contribution. And then these shadowing and anti-shadowing cannot be the same in the vector and the axial vector sector. Therefore, people have now started looking into this. But again, I am showing you the Minerva data and the different phenomenological results. See, the red line is the Jenny results, which has been shown by the bold red line. And then they have the error bars from the different simulations. And then you have the experimental numbers from the different Minerva observation of carbon to hydrocarbon, iron to hydrocarbon, and lead to hydrocarbon. And as you can see, even in the case of carbon to hydrocarbon, the experimental results are away from the Monte Carlo, and moreover, there is a big band even in the Monte Carlos. Therefore, whether you talk about this result or there is another result where I am showing, this is by Cloet, Bodek-Yang, Jenny, these are here. See the difference in the heavier nuclear target led to hydrocarbon, where the nuclear effects are expected to be large because the nucleus is heavy. There is a difference among the different studies, and also the Monte Carlos are different. Therefore, this also important it is important to study medium effects in the DIS region. Then we have recently also discussed this single Hyperon production by the anti-neutrino induced reaction. This I had told you that this process, because of delta X delta Q rule, is not possible in the case of neutrino induced process. But what we have shown in our recent works, that these processes are really very important for atmospheric neutrino studies, or in the low energy region like T2K and mini-bone, where the anti-neutrinos are in the energy region of 400 to 800 MeV. Because what happens, that these are the Hyperons. These Hyperons, they have got a longer lifetime, and they decay into a nucleon and a pion. Now, since they have a longer lifetime, therefore the pion which is produced faces less FSI effects. Therefore, in the case of delta, where that delta decays within 10 power minus 23 seconds and gives rise to pion, and that pion travels throughout the nucleus and it faces FSI effect, it may get absorbed also. The probability of pion FSI effect becomes very small because of the longer lifetime of Hyperon. And moreover, the Fermi and Pauli blocking effects are small in the case of Hyperon production. What we have realized and shown that if you plot the delta production and Hyperon production in the same graph, for example, here solid line is the black line is the pi minus production, and that dashed line is from the pions arising from Hyperon, and similarly this is for pi 0. As you can see, up to 500 MeV, Hyperon dominates over delta, and then even in the high energy region there is a dominance, it is non-negligible. While in the Jenny Monte Carlo till 2 years back this was not there. Now they are discussing with us and they are realizing that this should be a possible process which should be considered in Monte Carlos. And moreover, we have pointed out that for the mini boon or atmospheric neutrino energies, as you can see, we have put this a factor of multiplied a factor of 2.5 to the Hyperons to just show that the pions coming from delta and pions coming from Hyperon, this Hyperon contributes almost 40% to the pion production. Therefore, in this sub-GeV energy region, the production of pions from the Hyperons, these are very important. Therefore, there are many channels where not only you want to understand the free neutrino-nucleon cross sections, but when you move to nucleus, these nuclear effects become of different nature from quasi-elastic, where you have Fermi motion, Pauli blocking, RPA, and multi-nucleon correlation effect. When you go to inelastic resonance, you have pion delta resonance modification in the medium, pion production FSI effect, pion absorption. Then you have other inelastic scattering processes which contribute, where the nuclear medium effects should be studied. Then you have DIS process where the nuclear medium effects should be studied. Therefore, even in the theoretical sector, there is a lot of scope to work on the understanding of neutrino nucleus cross sections in the few GeV energy region. Although we have traveled a lot in the last 10 years to understand this energy region, but it's still miles to go. This road is long and terrain is really difficult. Thank you very much.
Thank you, Sajjad, for a very, very exhaustive and excellent talk covering a very wide range of topic, but at the same time, you try to kind of go in a slightly pedagogical way so that even the participants who are particularly the young students also get a grasp of things. There are lots of questions, so without much of taking time, I would like to go into questions.
Okay, let me first tell you, Satya, even if the students want to know something about this, these slides, or something about what is happening at the neutrino nucleus scattering cross section level, they can write to me separate mails. I will reply to them.
Sure. Perfect.
It will be my pleasure.
Great. Okay. So let us take a few questions at least right now. There are some on the YouTube and some on the Zoom call. So a couple of questions from Professor Athar. One of them I already kind of maybe you can answer directly yourself because
See, Athar,
just
Minerva flux has uncertainty because of the flux. Okay.
I just wanted to know roughly what is the percentage uncertainty.
Percentage uncertainty, I don't know exactly.
Is it like about 5%? Is it 10%?
No, it is more. It is more. Because see, the Minerva 6 JV data, they have not yet publicized. And reason for that is still that is a point which has to be well discussed and deliberated among those among the group itself themselves.
No, just continuing on that, do they use electron nu E scattering to get an idea of the flux, or is it some charge current process?
See, they are
In the
using
nucleon.
accelerator. They are using accelerators, where you have the production of pions, and then pions are decaying into muon type neutrinos.
No. Yeah, that's true. But what I'm saying is the flux of the neutrinos, is
Yeah.
that measured or is that estimated using new, let's say, scattering, electron scattering?
No. See, Data, the important point is, since pions are giving rise to muon type neutrinos, okay, and the detector in the Minerva case is very close by, because they want to have EMC kind of studies. Therefore, their target is not to study oscillation kind of studies. Oscillation kind of study is by NOVA and other groups. Okay, what they are measuring is the ratio of the cross sections for carbon to hydrocarbon, lead to hydrocarbon, and so therefore they are talking about muon type neutrinos only. The flux that they are talking
So the
about.
flux cancels out to first order, is it?
No, for the first flux does not
You
cancel
take
out.
ratios of cross sections, then.
See, actually, there is not exact cancellation because of the medium effects different in the different targets, and since the spectrum is quite wide, as I have told you, the 3 GeV region and the 6 GeV region is quite different, as you can see my curve.
Yeah.
And this is a very interesting study. This we did to show that really, see here, this is the 3 GeV region, their low energy region. And there are contribution from the various channels. And then they have this medium energy region that is around 6 GeV. And the contribution exactly becomes quite different, the different contributions. Therefore, there is the uncertainty is quite large, but exactly what is the number, I don't know. I can inquire about it.
Maybe we can. I'll send you a mail. So maybe in order that other people also ask questions.
See, the point is that even while I was in Japan and people were using T2K flux, they were not much willing to share the flux.
Okay.
And even in the 3 months of my stay, while working on atmospheric neutrinos, in the 3 months time, they changed the flux, I think 2 to 3 times in their internal discussions.
Okay.
So therefore,
Yeah.
yes, anybody else?
Yeah, Sajjad, I have quite a few questions from the YouTube, which means I have to read for you. But we may not be able to take all. I also shared your email in case they want to contact you. But let me take a couple of questions. One from Abhinav Chaudhary. Is Schwarzschild radius is also possible in respect of neutrinos like other matter particles? And can we treat neutrinos as matter particles like electrons, quarks, etc.?
I don't know much about Schwarzschild radius and the interactions.
Okay.
Because see, in general, neutrinos interact with matter. It interacts with electron, it interacts with a proton, it interacts with neutron. Okay, whenever we are talking about scattering cross sections, but what energies they have. Well, for example, if you talk about neutrino electron scattering, few MeV of neutrinos, the scattering cross section is 10 power minus 44 centimeter square. Okay, but if you go to low energy neutrinos, the scattering cross section really becomes very small.
Okay. There's one more question from the same participant, but I would suggest him to kind of see some of the old earlier talks. He talks about why neutrino oscillations take place. So this has been kind of covered quite well by previous speakers. I would like to skip that and move to another question by one by Sadashiv Sahu. In your atmospheric neutrino flux tables at energies greater than 11 GeV, how do you account flux with increasing opacity of Earth to neutrino with rise of energy?
See, the important point is, since I don't have only one slide on flux, let me just go to that. Yes. See, when we talk about neutrinos coming from atmosphere, one has to be very clear that when we talk about neutrinos of more than 10 GeV, okay, then pions are not the main source of those neutrinos, because pions becomes extremely relativistic, okay, and the source becomes the main source of neutrinos becomes kaons, and to those kaons then decay and gives rise to neutrinos. Then there is a density profile of the atmospheric neutrinos, and moreover, to calibrate all them, first the measurements were performed they have been used from the muons measured in the balloon experiments in the different heights. Even they have performed these muons measurements at the different altitudes and the different latitude, as well as different in the different regions, different latitudes as well as altitudes. And from there, they have calibrated their pions and kaons spectrum. So therefore, these are not just the basic input. There are many ingredients that goes inside the calculation of atmospheric neutrino flux prediction. If he wants, I can discuss with him in.
As I said, Sajjad, I did share your email with the participants. I'm sure for further questions they can ask you.
Yeah.
But I would say maybe I will take another one or maybe two questions at best, and then we'll close the session. So another question from the same participant, Sajjad. In scattering process, there is a provision of 4 pi directions, typically neutrino coming from the sun. It is practiced to use forward scattering. Is that concept fundamental, or is it just suitable in results?
See, the important point is when, for example, when we are placing a detector on the surface of Earth and it is in the direction of the sun, whether it is at Super K or at Sudbury, or the direction is direct, okay? Therefore, you have the neutrino flux theoretical calculations by the Bahcall model, and you know the amount of neutrinos coming per centimeter square per second from solar neutrinos. Say it is typically 10 power 6 neutrinos coming per centimeter square per second, and then that is interacting with a detector, and the detector. Therefore, you are directly saying it, the zenith angle bins in this case, directly you take that into account, that the interaction neutrino has come directly to it and it has interacted with the target, and a charged lepton has got produced.
Okay. So there are two more questions. The one on the that question I would like to post one. The question is there any model of neutrino deep inelastic scattering with the new LHCb pentaquark? Hopefully we'll have another speaker coming up soon.
I don't see these pentaquarks, etc. things I have not dealt with.
No. There. Hopefully we have a speaker coming up, so maybe we will we'll keep that for him. But the question that I'm going to ask you right now on behalf of the same participant is: what is possible of a high energy neutrino traveling in space, interacting with microwave background radiations with higher order loops? Sajjad, can you hear me?
Yeah. I'm able to. Yeah, I'm thinking about it.
Oh, yeah, thinking about it. Okay, fine.
Yeah, because see, microwave background, the energy is quite low. Okay, and these are basically the photons. Okay, the question. What was the question?
The question is, what is possible of a high energy neutrino traveling in space, interacting with microwave background radiations with higher order loops?
I think there will be some theoretical model calculations, but I have not seen those calculations.
Okay.
That is not my area of interest.
Okay. So that
Because these are the higher loop order loop calculations, and these are model dependent.
okay. So I guess there are just let me check once again. Yeah, I think there are no more questions now on the Zoom. Maybe some few questions will take up.
Yeah.
Just said. Therefore, Sajjad, once again, on behalf of all the participants, we'd like to thank you for taking your time and also giving this very exhaustive lecture on this, I think, very, very important topic for anybody working on any physics related to not only neutrinos, but also in general energy physics. And it has come so well, and I hope now, especially the younger participants will be probably benefited, as I said, more from your nice book, and they will also kind of take up the subject with much more.
Satya, 1 second. 1 second.
Yeah.
Zubair is there. Zubair, are you listening to me?
Yeah, I am here, sir.
Can you tell the uncertainty in the flux of Minerva?
Yeah, as the Athar sir was saying, Minerva uses Nu constraint to constrain the flux. And roughly for the medium energy, which Sajjad was saying about is 7 GeV, the uncertainty, fractional uncertainty is around 4.5%.
Okay. So I hope that has made things more clear. Yeah. So once again, so thank you very much, Sajjad. And so until Wednesday evening, where we are going to hear another interesting talk by Dr. D.K. Srivatsava. So thank you, everybody.
Thank you.
Thank
you so much.
Once again.
Thank you from Kolkata. Thank you.
Thank you, sir. Good night, everyone.
Good night.